Okay, so with our solubility charts, okay, what we want to do is we want to look up the negatively charged part of it on the top row, and then see where the positively charged part of it, or the metal in most cases, sits. Is it in the first row? Okay, if it's in the if it's in the second row, it's soluble. If it's in the third row, then it's not soluble at all. All right, so our first one is calcium sulphide, and of course you can't do that one because sulphide's not on your chart. Okay, keep forgetting to speak that one off. Okay. So, second one, potassium hydroxide. So hydroxide's on the far right-hand side, okay, and it says it is soluble with group 1 ions and ammonium. And we talked about what group 1 means, okay? Group 1 means basically the first column on the left, okay? Is potassium in that column? It is, okay? So this stuff, number 2, potassium hydroxide, is soluble. All right, for lead 2 chloride, all right, so we look up chlorine, okay, it's kind of in the middle here, all right, and it says it's soluble with most things, but I see that lead 2 plus is in the third row, okay, so this stuff would be not soluble. So this one is not soluble, this one is soluble, this one we couldn't do, okay. Tin 4 fluoride. All right, so we find fluorine. It's right next to the column we were looking at just a minute ago. Okay, it says it's soluble with most things. Okay, and I don't see tin in the third row, so this one is good. It's soluble. All right, copper 2 sulphide. Won't be able to do that one because sulphide's not on our chart. Okay, then we have potassium fluoride. Okay, so again we go back to fluorine. Okay, it says it's soluble with most things. Potassium's not in that third row, so that one is soluble. Okay, we got silver fluoride, lots of fluorine here. Okay, that one will be soluble because again silver is not in that third row. And then we have beryllium nitrates. Okay, nitrates in this second column here. Okay, it says it's soluble with most things except for these weird things at the bottom, of which beryllium is not included. Okay, so that one is also soluble. All right, that stuff will definitely be on tomorrow's quiz. Okay, there will be a couple of items like that where you have to use your solubility chart to see if it's soluble or not. And I promise I won't put any with sulphide in, because obviously you can't do this. All right, is that ringing a bell? Okay, so today we are moving on to probably the biggest concept in this unit, okay, and that is chemical reactions. So now we're going to be looking at, okay, what happens when two things go together, okay, what does that make? Okay, remember again that Dalton said that in a chemical reaction, okay, atoms can be separated, they can be joined, or they can be rearranged, but they can't be turned into new things. Right? So what we're going to have here is looking at how the atoms rearrange themselves or substitute themselves or whatever in a chemical reaction. We're going to be looking at 5 different types of chemical reactions. So today we'll look at the 5 types and learn kind of how to write them, and maybe even get to balancing them, okay, today. Right? And then we're going to be working on that for a couple of days, and then we'll move into how to predict the products of a chemical reaction. Okay, we'll work on that, and then we'll probably have a lab, maybe not this week, maybe next week. Okay, and then I'm looking at having your unit exam somewhere around the 11th of March. Okay, I'm going to solidify that at some point today. Okay, it'll be like the 11th or 12th of March. So you're getting more than 2 weeks notice of when it will be. Okay, but that's around when it will be. All right. Oh. I left all these notes on here. Okay, so signs of a chemical change. Now that you've spoiler alert, seen them all. Okay, signs that a chemical change has occurred. Okay, what are some of them? In case you didn't read them. Bubbles. Bubbles. Okay, if bubbles appear, that means what's been produced? A gas. Okay, so the production of a gas means that a gas wasn't there at the beginning, and something new has been formed. Okay, so that's why it's a sign of a chemical reaction. What's another sign of a chemical reaction? Temperature change. Okay, if energy changes either up or down, okay, that means that the chemicals involved have reached a different kind of energy state. Okay, a more stable state in that way. All right, what else? What are some visible ones? Color change. Yeah. Okay, if it changes color, there's definitely been something new produced, because if we had basically 2 things that were clear to begin with, and then suddenly we have something yellow, we have something with new physical properties. that means we have some new material that has formed. So basically all the signs of a chemical change are there because they signal us that new materials have been produced. Okay? Same elements, but new combinations, new materials, and as a result, we see different things with different physical properties. All right? So like we said here, signs of a chemical change, okay, could have color change, okay, we could have a temperature change, okay, we could have bubbles or a gas being evolved, okay. What else? Something to do with solubility. If I have a reaction and something's produced that's not soluble, what am I going to see? Starts with P. It's the name we give to stuff that falls from the sky. A precipitate. Okay, we could get a precipitate formed. Right? Again, a sign that something new has been formed because we may have started with things that were all soluble, and now we have something that's not. Okay, so again, evidence that we have new materials being formed. So all of these signs, and there are more of them, but okay, that's a good start at least. Okay, are signs that there has been a chemical change that has produced new materials. All right. Now, once a chemical reaction occurs, can you make it go back? Not in most cases, no. Okay? Like, for example, a fire is an example of a chemical change. Okay? It's the reaction of the molecules in whatever's burning with oxygen, and it produces carbon dioxide and water. Okay? I can't, like if I'm having a campfire, after it's burned, I can't get the wood and the oxygen back. Right? It's just not going to happen. That reaction has happened and I can't reverse it. Okay? Are there some that are reversible? Yes. But usually it involves me having to put in energy. Okay? For example, the process by which you discharge and recharge your phone. Okay? The battery in your phone, okay? That's a chemical reaction. As it discharges, okay, ions move from one thing to another, and then when you apply energy, force them to go back, okay, into a higher energy state, and then they can be drained again, and force them to go back. Okay, so there are some chemical reactions that can be reversed, okay, but obviously not indefinitely. I mean, eventually the battery in your phone craps out, and you've got to get a new battery on your phone or whatever. They conveniently time them so that your battery usually starts to give you trouble around the time your contract expires and you want to have a new phone. It's conspiracy. Okay, so we're going to look at the 5 types of chemical reactions. We're going to learn how to identify each type. Okay, each one is very unique. Okay, there's always something different going on, and then we're going to obviously learn how to write them out. Okay. So in a chemical reaction, the final products are chemically different from the starting reactants. So here's 2 terms that we need to know. Okay, products are what are produced in the reaction. Reactants are what we start with. They're the things that react with each other. Okay, so if I have, let's say, this kind of simple reaction. Let's say I have okay, so I'm going to have an acid-base reaction here between hydrogen bromide and potassium hydroxide. Okay, the product, so these here would be the reactants because they're the things that are reacting. Okay, and before the break, if you recall, I said if I write something down, you should definitely add it, right? Okay, so this is kind of an example here to illustrate the difference between reactants and products. Okay, so the products of this reaction are going to be water and potassium bromide. Okay, so these are our products. Okay, did I create any new elements? Okay, on the reactant side, I have hydrogen, I have bromine, I have potassium, I have oxygen and hydrogen together. Okay, over here I have hydrogen, oxygen, hydrogen, potassium, bromine. I haven't created any new elements because Dalton's atomic theory says I can't do that. Okay? All I've done here is rearrange the atoms. That's one of the things he said could happen in a chemical reaction. Okay? Now, are there going to be signs that this reaction has occurred? There are, okay? Because this stuff on the products are chemically different than the reactants. Okay? They're chemically different in this way. Hydrogen bromide is a strong acid. Potassium hydroxide is a strong base. Water is neutral. Okay? And potassium bromide is a salt. Okay? Anytime you add an acid and a base, they neutralize each other. They react. Okay? Their pH changes. That could also be a sign of a chemical change. Okay? Their pH changes and I end up with water and a salt. In any acid-base reaction, I end up with water and a salt of some kind, an ionic compound, okay, on the other side. All right? So the signs of this reaction would be a pH change, and there would probably be some bubbling and fizzing, and there would probably be a temperature change. Anytime you have an acid and a base react, they usually get pretty hot. All right? So all of those signs would be there, and they would all indicate that there is something new that has been produced. Okay? Everybody understand products and reactants? Okay, first and simplest type of chemical reaction that we're going to talk about are synthesis reactions. Okay? In a synthesis reaction, two elements are going to combine to form a single compound. Okay? Again, this goes back to Dalton's atomic theory. He said atoms can be separated, joined, or rearranged. This is a joining reaction. Okay? A synthesis reaction joins two things together to make one product. Okay? So some examples here. Okay? We've got magnesium reacting with oxygen to produce magnesium oxide. Okay, now the way this is written, you guys aren't going to have to worry about this part, but the S stands for solid, the G stands for gas, okay, S stands for solid, okay. The other thing you might see occasionally would be this one, aqueous, it just means it's a solution, okay. Most ionic compounds are written that way, okay. So you get an aqueous one, and you might also see L for liquid, okay. All right, so we would have those, okay, and then we also have these big numbers, okay. We got little numbers and we got big numbers, okay. Difference between the big numbers and the little numbers is this. Little numbers indicate atoms that are chemically bonded to each other. Okay, so anytime you see the little numbers, the subscript numbers, it means these two or more atoms are chemically bonded. When you see the big numbers, they indicate that there are two of this material. They're not bonded together, but there's two of them. Okay? So while they're saying a similar thing, there's two oxygens, there's two magnesium, they're telling me these oxygens are bonded together, these magnesiums are not. So essentially, these ones are holding hands, these two aren't. Okay? So the big numbers indicate I've got many of this, okay? And the little numbers indicate these things are together chemically. All right, now the reason we put in the big numbers is to make sure that our equation is balanced, okay? There's this thing in chemistry called the law of conservation of mass, or the law of conservation of matter, and it says that matter cannot be created and it cannot be destroyed, okay? So in a chemical reaction, I can't annihilate something, nor can I make it magically appear, right? So what it's saying is I have to have the same number of each type of atom on the reactant side and the product side, okay? And that's what these big numbers do, okay? On the reactant side of the equation, there are how many oxygens? 2, okay. Over here, the oxygen is now bonded to magnesium, okay? But are there still 2 oxygens? There are, because this number here, which we call a coefficient, okay, tells me there are 2 magnesium oxide molecules. Each magnesium oxide molecule has 1 oxygen atom in it. Okay, so there's still 2 oxygens. Everybody okay with that? Are there then still 2 magnesiums on both sides? Okay. This 2 means multiply everything behind me by 2. So there's 2 magnesiums, there's 2 oxygens. On this side there's 2 oxygens, and on this side there's 2 magnesiums. Okay, that's balancing a reaction. We balance a reaction to make sure we haven't created any matter or destroyed it. Right? That we have the same amount on both sides. Okay, so in a synthesis reaction, two elements, in this case magnesium and oxygen, react with each other and they form a single compound. Okay? Same with this example down here. Okay? So I have two potassium atoms. Okay? They're reacting with a molecule of bromine. Okay? And they're going to produce two molecules of potassium bromide. Okay? So this would be one molecule of potassium bromide. That would be the other molecule of potassium bromide. Do I still have the same amount of potassium and bromine on both sides? I do. The equation is balanced. Okay, this reaction has taken two elements and produced a single compound. Right? So synthesis reactions are the only reactions that start with two elements. Okay. All right. Questions on synthesis reactions? Okay. So two elements combine to form one compound. All right. The opposite of that. What do we call it when something breaks down? Longer word, starts with D. Decompose. Okay, so the opposite of this reaction is a decomposition reaction. All right, that means that a single compound is going to break down into its parts, into its two elements. So it's a synthesis reaction that's just reversed. Okay, so in a decomposition reaction, okay, we have a single compound that breaks down into its constituent elements. Sometimes it might break down into smaller compounds. Okay, that's also possible. If you have a really, really big molecule, it might break down into smaller molecules. Okay, but a decomposition reaction always starts with one reactant and one reactant only. Okay? These are not very common. The one you see up top there with the water, okay, that is actually the process by which rocket fuel is made. Okay, we electrolyze water to separate hydrogen and oxygen, which are the two ingredients in rocket fuel. Okay, they're cooled and liquefied and put in the big tank. Okay, so in this case here, okay, I start out with liquid water. Okay, I would arc electricity through it. That's what electrolyze means. Okay, you arc electricity through it, and it actually separates the hydrogen and the oxygen into their own elements. Okay, let's look and see if this reaction is balanced. How many water molecules are on the reactant side here? 2. Okay. How many hydrogen atoms are on the reaction side? You had the right number up. 4. Yes. Okay. So 2 times 2 is 4. So there are 4 hydrogen atoms on the reactant side. How many oxygen atoms are there? 2. Okay. Remember, this means multiply everything behind me by 2. All right. Over here, do I have 4 hydrogen atoms? And 2 oxygen atoms. So the equation is balanced. Okay, now, so this second one here, okay, we've got nitrogen triiodide, so the molecule kind of looks like this, okay, a nitrogen in the middle with iodine around it, okay. In this reaction, that breaks down into a molecule of nitrogen and 3 molecules of iodine. Nitrogen and iodine are some of the colored elements on your periodic table. If you just take out your periodic table and look at the non-metals, okay, you'll see that it's color-coded. Okay, anything that's yellow comes as a 2 when it's by itself. These are what we call the molecular elements. Okay, so they actually form molecules with themselves. Okay, so that's why the nitrogen has a 2 and the iodine has a 2. Okay, they actually form molecules with themselves. Okay, is this reaction balanced? Okay. How many nitrogen on the reactant side? 2. How many nitrogen on the product side? 2. Okay. How many iodine? 6. 6. Okay. So they're all balanced. Okay. Questions on decomposition reactions? Okay. So a decomposition reaction always starts with one compound and breaks down into 2 elements or 2 compounds or a compound and an element, but it's always breaking down. Okay. Most of the time it's going to be into 2 elements. All right, now, this is where things get a little crazier. Combustion reactions, okay? In a combustion reaction, we have what we call a hydrocarbon, okay, which is a compound containing carbon and hydrogen, hydrocarbon, okay, reacting or burning in the presence of oxygen, okay? the products of any combustion reaction are carbon dioxide and water. Okay, so a combustion reaction always goes with this pattern: carbon and hydrogen plus oxygen. Okay, so there'll be some compound, okay, with carbon and hydrogen in it reacting with oxygen gas. Okay, and that will always, the products of this reaction are always the same: carbon dioxide and water. All that changes is how much carbon dioxide and how much water will be produced. Okay? The bigger the molecule you burn, the more carbon dioxide is going to be produced. Okay? This is one of the reasons why countries are looking, if they're looking to reduce the amount of greenhouse gases they produce, they look to eliminate things like coal, okay, like burning coal to make electricity, and replacing it with things like burning propane instead. Okay? Because coal is a much larger hydrocarbon molecule. Okay? This is propane right here, C3H8. Okay? Coal is like C18 or something like that. Like, it's a much bigger molecule. So when you burn it, you produce way more carbon dioxide, okay, than you do with propane. All right, everybody with me here so far? Okay, so in a combustion reaction, it's always carbon, hydrogen plus oxygen. Okay, it'll actually look, if you're writing a formula, it'll look like this: CnH 2n plus 2. So hydrogen's always going to be twice carbon plus 2, right? So 2 times 3 is 6, plus 2 is 8. Okay, and then it'll be plus oxygen, whatever you need. Okay, and that'll always make carbon dioxide and water. Right? So you never have to figure out what the products will be. They're always the same. Combustion reaction always produces carbon dioxide and water. Okay? And that's why on a really cold day, you can see water dripping out of a tailpipe of a running vehicle. Okay? If it's really, really cold outside, the water vapor will condense inside the exhaust pipe, okay, on its way out, and it'll just drip, okay, out of the exhaust pipe. Okay? That's clean water, okay, that's coming out of the engine. Okay? All right, now for balancing. Combustion reactions have special rules to balance them. Okay, all other reactions are balanced fairly easily. Okay, combustion reactions always involve a separate set of kind of instructions or steps for balancing. Okay, so what we're going to do is kind of look at those steps here. Okay, so I'm just going to put a reaction up here. Actually, no, I don't want to get that one. We'll use the one that was up there. Okay, so right now, is this reaction balanced? And by balanced, I mean, do I have the same number of carbon and hydrogen on both sides? I don't. Okay, over here I have how many carbons? 3. How many do I have over here? 1. Just 1. Okay, so right now it's not balanced. Okay, same with my hydrogens. I've got 8 hydrogens over here, and I've only got 2 over here. And right now I've got 3 oxygens on this side and only 2 over here. It's a mess. Okay, it's nowhere near balanced. Okay? So I'm going to need you to write down these special balancing rules for combustion reactions. Okay, so we'll just say it's combustion reaction balancing rules. By the way, RXN is the abbreviation for reaction if you want to save yourself time. Okay. All right, rule number 1 for balancing combustion reactions is that we are going to balance them alphabetically. Okay, that means we start with carbon, then hydrogen, and finish with oxygen. Always. If you don't do it that way, you'll never get it to balance and get really, really frustrated. All right? Okay, so I'm going to balance this thing alphabetically. All right, so I've got 3 carbons on this side, and I've only got 1 over here. Okay, I can't put a 3 here because that would change the molecule. but I can change how many of those I have by writing a 3 here. Okay, by writing a 3 there, I'm now saying I have 3 carbon dioxide molecules. Okay, and while that balances my carbon, it also gives me more oxygen, but I'll deal with that later. Okay, now my carbons are balanced. What comes next? Alphabetically. H. Okay. On this side, I have 8 hydrogens. What do I need to write in front of water to get 8 hydrogens? 4, because 4 times 2 will be 8. All right. Now, my hydrogens are balanced. Now I'm going to balance my oxygens. Okay. How many oxygens are there here? 6. How many here? 4. Okay, so I've got 3 times 2 is 6. So the carbon dioxide has 6 oxygen atoms, and there are 4 more oxygen atoms in the water for a total of 10. Right? 4 plus 6 is 10. What times 2 will give me 10? 5. Okay, that's balancing. Making sure I have the same number of everything on both sides. Okay? So, combustion reaction balancing rules. Rule number 1, balance alphabetically. That worked great for this one. It won't work as good for this reaction. We're still going to balance alphabetically. That won't change. Okay? But if I have if I follow that rule with this reaction, I'm going to run into a problem. Okay, so just kind of follow along with me here. I'm going to balance my carbons first. There are 4 of them here, so I'm going to put a 4 there. Okay, on this side there are 10 hydrogens. I'm going to put a 5 here. Okay, now my hydrogens are balanced. So I have 4 times 2 is 8 oxygens, plus 5 more is 13. Okay, so I have 13 oxygens over here. What times 2 gives me 13? Yeah, 6.5. Can I have half a molecule? No, I can't have half a molecule. Okay, so that doesn't work. So what I have to do instead is I have to put in what I like to call, if you're a Star Wars fan, you'll know where I'm going with this, the rule of 2. Okay? If you're not a Star Wars fan, that went right over your head, that's fine. Okay? The rule of 2 says if I have an even number of carbons, I start balancing with a 2. Okay? Okay, start my balancing with a 2. Because if I double everything, will that get rid of the 0.5? Yes. Okay, because half doubled is a whole. Okay, so I'm going to start my balancing with a 2. Okay, now I'm going to do the alphabetical thing again. 2 times 4 is? 2 times 4 is 8. Okay. Yeah, it's okay. We're rusty. We had a week off. Okay, so 2 times 4 is 8. So now my carbons are balanced. 2 times 10 is how many? 20. Okay, what times 2 gives me 20? 10. All right, so now my hydrogens are balanced. I've got 20 hydrogens on both sides. Now I'll look at my oxygens. 8 times 2 is 16. Okay, and another 10 more is 26. What times 2 gives me 26? 13. Okay. Now I eliminated that whole, I have a decimal problem. Okay? Because you can't have a decimal when you're balanced. All right, so those are special balancing rules for combustion reactions. For every other reaction, there's only one balancing rule. Start with the biggest number first. Go from there, okay? And we'll go back and forth. We'll look at that, okay? There just is this hard set of rules for combustion reactions. Okay. So the way we recognize a combustion reaction, we look for carbon and hydrogen burning in the presence of oxygen. Products are always going to be carbon dioxide and water, no matter what. All right. Questions on combustion? All right, so we got two reaction types left, and they're very similar. Okay? They both involve ionic compounds and being rearranged. Okay? So in our first one, we have a single replacement reaction. Okay? In a single replacement reaction, an ionic compound, and it has to be ionic, there will be no molecular compounds in a replacement reaction. Okay? An ionic compound will react with an element. Okay? In that replacement reaction, the element will replace part of the ionic compound. Okay? And it'll replace whatever it's like. So if this ionic compound reacts with a metal, the metal will replace the metal in the compound. If it reacts with a non-metal, that non-metal replaces the non-metal in the compound. Right? And so the pattern ends up looking like this. So as our example here, I have copper metal reacting with silver nitrate. Okay, so basically this reaction looks like a solution, a clear solution of silver nitrate, and you put copper in it. So a piece of copper wire, or, well, you can't get pennies anymore, but if you had a penny, okay, you could, anything that was made of copper, you plop it in there. Okay, leave it in there, and the next day you'll come back, and that copper will be replaced with silver. Okay? The alchemists would have loved this reaction if they could have made it work. Okay? Because it would have actually made it look like they could turn copper into silver. Okay? If you did this with a penny, you'd come back the next day and silver would be plated out on the penny. Okay? The penny wouldn't turn completely to silver, but it would be covered with it. Right? Now I know you're thinking, where can I get this stuff? Because that sounds like a way to get rich. Silver nitrate's really expensive because it's got silver in it. Okay? So it's not something you're going to get rich on unless you steal it. Right? But yeah, so in this reaction, okay, what happens is the metal replaces the metal that's in the compound. Okay? And so silver ends up by itself and copper ends up with nitrate. Okay? If this reaction had been a non-metal reacting, then it would have replaced the non-metal. All right? So what it actually ends up looking like is kind of like this. There's this guy standing by himself. There's this couple dancing. This guy likes her. So he rolls this guy, tosses him out, and takes off with his girl. Or it could go the other way. It could be a girl by herself, and she gets the other girl gone and takes off with the guy. It could work either way. Okay? Whatever's alone is going to replace what's like them in the couple. Okay? Now, this is where the analogy breaks down. Chemistry is old-fashioned. Okay? This always has to be a metal and a non-metal in the compound. It has to make an ionic compound. So you can't have two guys run off together, you can't have two girls run off together because chemistry is old-fashioned. Okay? It has to make an ionic compound, which is a metal and a non-metal. Okay? And that's where the analogy breaks down. Not that there's anything wrong with that, but the analogy breaks down. Okay? All right. Everybody okay with that idea? Okay, so in a replacement reaction, okay, an element reacts with an ionic compound, and what's produced is a new element and a new ionic compound. All right, so this would be an example of one that involves a metal, okay, and then this would be one that involves a non-metal. So I could have chlorine gas reacting with, let's say, potassium oxide. Okay, so is chlorine a metal or a non-metal? It's a non-metal, right? It's a gas. Okay, so who is it going to replace? Who is potassium going to end up with? Okay, what's the non-metal in this compound here? Oxygen. Okay, so chlorine is going to replace oxygen. Okay, so that means that now potassium is with chlorine and oxygen ends up alone. Okay, so but there's always something getting replaced. One thing only. That's why it's a single replacement reaction. One thing gets replaced, right? And then I would have to make sure this is all balanced. Okay, how many potassium are on this side? 2. How many are over here? Just 1. So I have to put a 2 there. Okay, now I have 2 potassium, but I also have 2 chlorine. Go back over here. I've got 2 chlorine. Now is my equation Balanced? No, it's not. Okay, so let's try that again. All right. So I've got 2 oxygen over there. What do I need to put here in order to make 2 oxygen? Okay. How many potassium does that give me? 4. Okay, now I'm going to try this. Okay, now I've got 4 potassium. How many chlorine do I have? 4. What needs to go here? 2. Okay, that's how you balance every reaction type other than combustion. Pick one, start with it. Just keep going back and forth until you've got the whole thing balanced. Sometimes you'll run into the problem I ran into, which of course I did on purpose. But okay, you'll run into a problem where you're like, oh, that didn't work. Erase it, try it again with something else. All right. Okay, so that's single replacement. Okay, so remember, in a single replacement, only one thing gets replaced. The last kind, double replacement. Okay? In a double replacement, 2 things get replaced. So instead of having an element and an ionic compound, in a double replacement reaction, we have 2 ionic compounds. And basically, it's 2 couples dancing, and they just switch partners. Okay, so I end up with 2 new couples on the other side. Okay, so in a double replacement reaction, okay, 2 ionic compounds in solution react with each other and essentially trade ions or trade partners. Okay, so in our example here, I have calcium chloride, calcium being the metal, chlorine being the nonmetal, sodium carbonate, sodium being the metal, carbonate being the nonmetal. Okay, and all that happens is the metals switch places. Okay, that produces 2 new couples or 2 new ionic compounds on the other side. Okay, so calcium, who was originally with chlorine, is now with carbonate. Sodium, who was originally with carbonate, is now with chlorine. And done. Okay, this reaction actually produces a precipitate. Okay, it starts out as 2 solutions and produces a precipitate. Okay, calcium carbonate is chalk. Okay, it's not soluble in water. Okay, everybody all right with that one? I'm going to write another one up here, and we're going to look at some balancing stuff. Okay. So let's go with. Okay. So, if I'm balancing this reaction here, what should I start with? Okay. Always start with the biggest number. Okay. Biggest number in this reaction is 3. Right? Magnesium's a 3 on this side, potassium's a 3 on this side. Okay? Now, I'm going to go with balancing magnesium first, just because it's a gut instinct for me. Okay? It's a 3. All right, so I'm going to come over here. How many magnesium do I have here? Just 1, right? There's no little number next to it. Okay? So there's 1 magnesium here. So I'm going to need to put a 3 here to balance my magnesium. Now, when I do that, how many nitrate do I have? Without this 3, how many nitrates are there? 2. So I have 6, right? This means multiply everything behind me by 3, right? So there's 2 nitrate ions. 3 times 2 is 6. How many nitrate ions are over here? 1. This is the tricky part, okay? Remember, this 3 doesn't mean there's 3 nitrates, it means there's 3 oxygens, okay? Nitrate is NO3. There's 1 nitrate ion over here, and I have 6 of them over here. So what needs to go here? How many nitrates do I have here? 1. How many do I have over here? 6. What do I need to put here? 6. Okay, I need to put a 6 here. Okay, remember, I'm essentially saying this, right? There's 1 nitrate. Okay, now there are 6 nitrates, but now there are also 6 potassiums. All right, so I got to go back over here. I only have 3 potassiums here. What do I need to multiply 3 by to get 6? Okay, and when I do that, that gives me how many nitrogen? 2 times 1 is, are there 2 over here? Always a good sign. If when you're down to the last one, it works, then you did the whole thing right. If you get to the last one and it doesn't work, then you get to erase it and start over again. Okay? But this time we did it right. Okay. This is the tricky part though. Okay? Dealing with the polyatomic ions always confuses people. Okay? Remember, this 3 just means there's 3 oxygens. There's 1 nitrate, or in this case there's 2 nitrates. Okay? Over here, there's 1 nitrate. Okay? Don't get them confused, that's the tricky part. All right, don't worry. I'm going to spend lots of time on this. Right now you're probably going, deer in the headlights, but it's okay. Okay. All right. I'm going to give you a little deer in the headlights break. I'm going to give you about 4 minutes, and then we're going to look at doing a few reactions ourselves here, okay? So when we're writing out a chemical reaction, okay, there's 2 ways that we might write those, okay? This way, which involves just the formulas of the compounds, and we might also write a word reaction, which would basically be just writing the names out, okay? When we write it out in formula form, we do have to communicate how much of everything there is. That's those big numbers, the coefficients, okay? And ensure that the reaction is balanced, all right? So a properly communicated chemical reaction looks like the example here, okay? Where I have 3 molecules of nitrogen dioxide reacting with 1 molecule of water, okay, to produce 2 molecules of hydrogen nitrate and 1 molecule of nitrogen monoxide. Okay, this reaction is balanced, okay, because on this side there are how many nitrogen atoms? Okay, how many nitrogen atoms in nitrogen dioxide? 1. Okay, but there's a 3 in front of this, so there's how many nitrogen atoms? 3. Okay, on this side of the reaction, there are 2 nitrogen atoms here, and there's another one here for a total of 3. Okay, so the nitrogen is balanced. There's 3 on both sides. Okay, for the oxygen, okay, there's 3 times 2 oxygen, so there's 6 there, and there's 1 more there for a total of 7. Okay, and then on this side, there's 2 times 3 is 6, plus 1 more is 7. So the oxygens are balanced. Okay, and so are the hydrogens. There's 2 hydrogens here, and there's 2 hydrogens here. Right, so the reaction is balanced. Okay, so in a balance or a balanced chemical equation is one in which the total number of each kind of atom or ion in the reaction is equal to the total number of the same kind in the product. So basically the reactants and the products have to equal each other. Okay. All right. So, left the answers up there. Okay, I want you guys to try question, just the first reaction right now. Here's what I want you to do. Identify what type you think it is. Synthesis, decomposition, combustion, single or double replacement. I want you to write it out in words, so write the names, and balance it. Okay, just try that with the first reaction. I'll give you a couple minutes and then I'll show you what it looks like. Okay, so first off, what kind of reaction are we looking at here? We've got 2 elements and they're reacting to form a single compound, so this is a synthesis reaction. All right, so that's the first thing we want to write. Okay, that's a synthesis reaction. Okay, if I'm writing it out in words, all I'm doing is naming everything. Okay, this stuff is nitrogen. Okay, what's this stuff? Hydrogen. Okay, and this stuff is nitrogen trihydride. Okay, it's molecular, okay, because hydrogen comes second. All right. Now I've got to balance it. What should I likely balance first? mean, our rule has kind of been balance the biggest number, right? Okay, the biggest number is 3. But on this side, so I've got 3 hydrogens over here, and on this side I only have 2. Okay, what's a number I can use that they would both go into? Like, what's the lowest common multiple? Okay, what is 2 times 3? Okay, that's the lowest common multiple. Okay, it's the number they both go into. All right, so if I put a 2 here, that'll give me 6 hydrogens. Agreed? Okay, what do I need to put in front of this to make 6 hydrogens? 3. 3 times 2 is 6, right? Okay, now, when I put this 2 here, that made 6 hydrogens, but it also made how many nitrogens? 2. Are there 2 over here? Again, always a good sign when I get to the last one if it's already worked out. Okay, so that's the balancing there. All right, I want you guys to try the next one. Okay, same thing. Tell me what type it is, write it out in words, and see if you can balance it. Okay, I'll give you a couple minutes and we'll go through it together. Okay, so in the second one I have nitrogen, which is an element, reacting with calcium chloride, which is an ionic compound. The products are calcium nitrate, an ionic compound, and chlorine, an element. So what reaction type that we went over starts out with an element reacting with an ionic compound, producing an ionic compound, a new element? Right, which one? Which reaction type is that?
Single.
Single replacement. Okay, so this is a single replacement reaction. Okay, so we're just going to go SR. Okay, now we've got to write it out in words, which is basically just a naming exercise. Right, so we have nitrogen, okay, plus calcium chloride. Okay, and you don't have to write like a sentence or anything, just write the pluses. Okay, sorry, it's going to give us calcium nitride and chlorine. Okay, now we have to balance it. What should I balance first? Bigger number, which would be calcium. All right, so let's start with that. On this side, I've got 3 calcium. Over here, I only have 1. So what times 1 is 3? 3, right. Okay, so I'm going to put a 3 here. When I do that, it gives me how many chlorines now? 6. 3 times 2 is 6. All right, so I'm going to go over here. What times 2 will give me 6? 3. Okay, and then I'm going to look at my nitrogens. There's 2 nitrogens here, and there's 2 nitrogens here. So is everything now balanced? Good. Okay, start to make a little more sense. It just takes practice. It's unfortunate. It's just one of those things where you got to put in the time. Okay, try the third one and the fourth one here. Okay, now the third one is a little tricky because it's, spoiler alert, what kind of reaction? I've got a carbon hydrogen containing compound reacting with oxygen producing water and carbon dioxide. It's a combustion reaction. Remember, we wrote down 2 special rules for balancing those. Okay, give you a few minutes on those ones. So we said this one's a combustion reaction, right? We're going to write out the names of everything. This is carbon tetrahydride. Okay, reacts with oxygen. Okay, gives water and carbon dioxide. Now, for the balancing part, okay, we had 2 rules. Balance alphabetically and the rule of 2. But the rule of 2 only applies if I have an even number of carbons. I have 1 carbon. Is that even or odd? 1 is odd, so I don't have to apply the rule of 2. Okay, so I've got 1 carbon and 1 carbon. So carbon's already balanced. I've got 4 hydrogens here, but how many here? Just 2. So I need to put a 2 in front of this to get me my 4 hydrogens. Now I've got to look at my oxygens. I've got 2 oxygens here and another 2 here for a total of 4. 2 times 2 is 4. Okay? So remember, we balance that one alphabetically. All the others we go biggest number first and we go from there. Okay? All right. Tomorrow, your quiz is going to have some naming and solubility and maybe some properties of compound stuff. Kind of a review of everything we did before the break. Okay? We're going to do that, and then we're going to come back to reaction types and work on balancing and all of that kind of stuff. Okay, so that'll be the bulk of tomorrow. I will post some questions by the end of the day. Okay.